Hello, in this video we are going to go over how to use your 3D data to assign both the backbone and side chains of a protein. We will also cover how to use chemical shift predictors such as SPARKY to assist an assignment. We will then cover how to convert your data to an NMR star format for BMRB deposition and to run Talos to check backbone assignments. Finally, I'm also going to go over some tips and tricks on different ways to use your 3D data to try and get the most information you can out of them. I want to preface this by saying this video is not an in-depth tutorial, but rather a surface-level guide that will cover more the philosophy and theory for assignments than the exact details on how to set up and troubleshoot specific programs or experiments. Now, I'm going to take a different approach in this video than typical. Usually, theory is covered first, then you move on to practice. I'm going to assume you already have your data processed and ready to use. So instead, I'm going to go over practice first, show you how to set up your strips and spectra, then go into the theory of what these experiments are actually showing you. So I'm going to be using NMR Box, which is a platform that has multiple different programs for NMR assignment and analysis of various data such as relaxation data pre-set up and configured to work. And in this NMR Box, the program that I'm going to use is called SPARKY. Now, there are multiple different programs that you can use for your assignments. So you can use Cara, I believe there's NMR FX, CCP NMR, NMR Vue.j, but I use SPARKY because my PI uses SPARKY and everyone in my lab uses SPARKY. So to run it, you just go to the terminal and type in SPARKY. So the first thing that we're going to want to do is cover how to assign your backbone. And so we're going to first have to open our NHSQC. So to do that, you can just go to File and Open, and then navigate to the directory that contains your data for your NHSQC. So for me, it will be over here, and we're going to get this N15 HSQC. Now, SPARKY can open any .dat file, and then it will convert it to a UCSF file. So if we click Open, here we can see our NHSQC. Now that we have our NHSQC open, we'll want to open our 3D data. And for the very first one, I'll start with the HNCA. Now you can go to File and Open, and again, navigate to the folder that contains your HNCA experiment. So for me, that'll be over here. And again, there's a .dat file. And then do you want to convert this to UCSF? You'll click Yes. So this will take a quick second for it to convert the .dat to .ucsf, and then you'll see your 3D data will open here. Now, the very first thing that you want to do is to sync up your HNCA and NHSQC. To do that in SPARKY, you click YT. You want the nitrogen dimension in your HNCA here to be the one that allows you to go through multiple planes, and you want that synced up with the NHSQC. And so to do that, you just click on the N15s and then click Synchronize. You also want the proton dimension also synchronized. So let's cover here what we're even looking at to begin with, right? What is this strip? What is it showing? So I like to use this proteinnmr.org.uk site. I think it's really nice in terms of explaining both 3D data and 3D experiments and describing what they are, how they work, and what you can see. So 3D data essentially has your nitrogen and proton information. Let me move this over here so you can see the HNCA in two of the dimensions, and then the carbon is in the third. You can think of this as your, I guess, y-axis. They have it set up here, right? So for every peak you see here, you're going to have a strip that you see here that is going to have the carbon information for the experiment that you've run. So to show an example of this, what you have to do first is pick your peak, right? The way this is done here is if you go to the pointer mode in Sparky, there's an option here to find and add peak. And we can just click on any peak here. So I'll click on this one here. And if you click VC, if you recall, we synced up the HNCA with the NHSQC earlier. So what it does is it converts the nitrogen dimension here to the nitrogen dimension in your NHSQC here. So 120.3 and then 120.3 here. And also the proton to whatever the proton dimension is here. So this is 7.175 and you have the same thing here, right? And what we'll see is basically a strip. Let me make this a little more narrow and let me make this bigger so it's easier to see. So you see this one strip and you'll see you have a carbon value here that corresponds to it, right? That is essentially what we're seeing here. And we should see, oh, there's only one peak here in this strip. Now, something that you may also want to do is play around with the contour levels. And to do that in Sparky, you can click CT, and here it shows you your contour level. So we want to go further down into the noise. Maybe peaks will start popping up. Oh, that's for the NHSQC, sorry. Make sure you change the view up top here to be the HNCA. Oops, this should be 3E. And if I go further and down the contour level, you can see another peak has started to pop up, right? So this strip corresponds to this nitrogen, to the amide backbone of this amino acid. And in this experiment, we're looking at an HNCA. So what an HNCA shows you is the alpha carbon of the I and I-1. So again, if we use this site, they have a nice set of diagrams for triple resonance experiments. So if we go to an HNCA here, we can see it effectively tells you the same thing. The HNCA correlates the amide backbone with the C alpha carbon of the I and I-1. Now to explain some nomenclature, the I is the amino acid that contains that nitrogen, or it's the amino acid of the peak that you're looking at here. The I-1 would be the alpha carbon of the preceding amino acid. And in each strip, if we go lower, you'll see an example here. You should have two peaks. One that is the I, one that is the I-1. Now usually the I peak will be stronger than the I-1. This is not always the case, but typically that's how it works. So in this case, we have your I peak here at around 60.45, and your I-1 is at around 56.9. So now we have the chemical shift information for the alpha carbon. But how can we use that to assign our amino acid? Now there are two foundational principles when it comes to assignments, two questions that you have to be able to answer. The first is, what is the amino acid of the amide that we're looking at? And the second question is, where in the sequence is this amino acid? So we can answer both of these potentially using the 3D data, such as our HNCA. Now, we can look at the average chemical shift value of the C alpha carbons, the alpha carbons, for each amino acid. Right, so in this case, we can see here, this bar represents the range that alpha carbon, the range of chemical shifts that alpha carbon can have. So for example, for valine, the alpha carbon ranges between 60 to 66. For alanines, it ranges between 51 to, it looks to be here, 55, right? So in our case, we have amino acid, or we have a alpha carbon chemical shift at 60.48 for the I peak and 56.87 for the I minus 1. So the I peak could potentially be a valine, as we can see here. It might be a proline, might also be an isoleucine, or threonine as well. For the I minus 1, it could be, as you can see, a whole range of potential things. This is often why the HNCA alone is actually not enough to assign a protein, because you can see the C alpha values often are overlapping, and you'll need more information to be able to answer, again, those two underlying questions of what kind of amino acid do we have and where in the sequence is it. This is why oftentimes you run experiments that also give you the C beta. And that experiment is called the HNCACB. So let's open that one up as well. And we open it the exact same way as we did the HNCA. So here I'm going to go find my HNCACB. And I'm going to open it. And again, it will want to convert this .dat file to a UCSF. And this will take just a couple of seconds to open up and convert. And here, let me minimize this. Here is our HNCACB. And so let me make it narrow into a strip. And again, you'll want to synchronize this just like you did the HNCA. So you'll want the nitrogen synced up with the nitrogen of the NHSQC and your hydrogen synced up with the hydrogen of your NHSQC. So now let's go to a strip. Same way, we'll use VC to go to the strip for this amino acid. It's HNCACB. And we'll notice here we have one peak here that's positive, and we'll notice a peak here that's negative. Now, the way I know this is if I do contour levels, here you can see the color of your positive and your negative. I like to go a little further down into the contour level here. Sometimes peaks will, as we saw before, start popping up. So in this case, now we see a new peak pop up here at 31. And if we go down here, we can see another peak showing up at 56.87. Now you may have noticed that the chemical shift of this peak here at 56.87 is identical to what you see in the HNCA. You'll notice the same thing here. Chemical shift here at 60.5 is the same as in the HNCA. Let me move these over here to make some room. And the reason for this is, well, the HNCACB also shows the C alphas for your I and I minus 1. But it also shows the C betas. So if we go back to this window here, let me go up and let's bring up the description for the, where is it? HNCACB. So you can see here that this experiment shows you the C alpha and C beta of your I and I minus 1 amino acids. And so what you would expect to see is generally 4 peaks, right? Your 2 peaks for your I, C alpha and C beta, and then 2 peaks for your I minus 1 C alpha C beta. And in this experiment, these peaks, the C alphas are going to show up as positive and the C betas are going to show up as negative peaks, which is why they're green here. It might be easier if I give a black or white background to these. You might be able to see them better in this video. Right. So now we see we have our 2 C alpha peaks and 2 C beta peaks. And this works similar to what we covered earlier about the HNCA. The stronger of the 2 peaks is going to generally be the I C beta, and the weaker one will be the I minus 1. So now we have a C beta at 34.55 and a C beta at 31.04 for this particular peak. And now if we look at our table of chemical shift values, we can see here that based off the data we have, we can start to answer that first question. What is the type of amino acid that we have here? So we have a C alpha at 60.45, which is either valine, proline, or isoleucine. And we have a beta now at 34.5. So if we look at our list here, we can see that this could potentially be a valine. It could potentially be a proline as well, although this is a little outside of the range for the beta. And we can see now that it's definitely not a isoleucine based off the value of its chemical shift. So right off the bat, we have a good idea of what type of amino acid this is based off just using an extra experiment that gives us the C beta. The I minus 1 has a C alpha at 56.9 and 31.1. And so immediately we can cross off a couple of potential amino acids that the I minus 1 might be. It's not an alanine because while the alpha, actually it's not an alanine because neither the alpha or beta are in range. It's not an asparagine or aspartic acid because while the alpha for those is in range, the betas for those are usually much higher, as you can see here. What is it at? Yeah, 31. It could potentially be an arginine. It could potentially be a cysteine, glutamine, a glutamic acid. It could potentially be a histidine. So you can see that by itself, again, having even the C beta is not necessarily enough to just determine exactly what this I minus 1 amino acid is. But the next question that we're going to answer can help us identify what amino acid this is. And that is, where in the sequence does this amino acid show up? Now naturally, to do this, you're going to need your sequence. So let me get rid of that and bring my sequence over here. So as we said earlier, we have a valine or proline, and its I minus 1 could be a number of different things. Now this is the sequence of my protein that we're looking at here. It's 242 amino acids. And if we look at just a search of all of the valines, now we can start to see where in the sequence this might be. Right, so we have a valine here whose I minus 1 is a glutamine. And so as we said earlier, this could be a glutamine. So this could potentially, or this amide peak could potentially be valine 5, as you can see here. Here we see we have 2 valines. One whose I minus 1 is a valine. That's clearly not what's going on here. And this other valine, its I minus 1 is an aspartic acid. As we covered earlier, the aspartic acid C beta would be higher. So we also don't have that going on here. Here we have a valine whose I minus 1 is a histidine. And we said this I minus 1 could also be a histidine, so we don't have that going on. And I won't go through everything since there's quite a number of valines, but we can see it's not valine glycine. If I bring up this sheet here, glycine doesn't even have a beta, so it's definitely not that. But there are a couple different matches, right? This could be a valine lysine, right? And we have another valine lysine here, could be valine glutamic acid. And we also said that it might be a proline, and we can see we have multiple prolines. Now, I said that just based off of looking at the chemical shifts. But there are other factors you have to keep in mind. For example, prolines would not show up in your NHSQC. And the reason to understand why is if we just look up proline and a peptide backbone, here we go. So you can see here this proline here, there's no hydrogen there. So you won't actually see it in your NHSQC. And so as we covered earlier that this is the I that we're looking at, it can't actually be a proline because you'll never see the I amide for the proline. So we know we have just a valine, but as we saw, if I go back to this valine, we have a lot of different potential things that this valine could be. And so this is often why that we don't actually start when it comes to the assignments with these amino acids that are potentially valines or leucines or isoleucines. Generally, we like to have amino acids that have very distinct chemical shifts and distinct positions. And these are known as anchor points. And these anchor point amino acids usually are alanines, since alanine is the only amino acid that has a beta that is below 20. We also like to use threonines, since they're also the only amino acid that has betas that are above the 60s. Serines are also good because their betas are also the only ones that are above 60. So these are general anchor points, such as glycine as well. You start with them and try and see if you can assign them. Now, if we go back to this site here and go to the NHSQC, some types of amino acids show up in particular regions. So here they say your asparagine and glutamine side chain NH2 groups oftentimes show up here. You can see I have the same thing here. These are not amide backbones, but this NH2 side chains. You have tryptophan side chains that usually will show up way over here at the end of your spectrum. You can have your arginine folded side chains. And you can also have a C-terminal amino acid that is generally pretty strong, and it's generally in the bottom half of your spectrum here. But what this doesn't cover is specific groups oftentimes have a tendency to show up in certain regions. For example, generally glycines show up between the 100 to around, we'll say 110 ppm range in nitrogen, and they generally show up between 9.5 and I've seen them as low as 7 ppm. And these are good anchor points to start with. Usually I've seen threonines and serines show up right here in this region between 112 ppm to around 116 and we'll say 9 ppm to about 7.5. So again, these are good anchor points that you can start with. And like I said, we can use the HNCA and HNCACB to identify them. So again, the first thing that you're going to want to do is pick the peak, type in VC, and jump to the peak here. So if we look in this scenario, like I said, this is usually where threonines and serines show up. And we can see we have a C beta at 63.86 and a C alpha at 60.35. And if we look at the list of ranges, we can see that this is undoubtedly 63, either a serine or a proline. Or sorry, serine or threonine based off of this value. So we immediately know it's one of these two. Oops. And let's see if we have an I-1 here. And we have an I-1 that is at around 18.5 for C beta and 54.5. So we also know that this is without a doubt an alanine. So now if we look at our sequence here, what we're looking for is a threonine, which we have multiple, that precedes an alanine. So in this case, I'm looking for ATs. And I see I have only one instance. Now, there's also the potential chance that this is also serine. So we also want to look at a serine preceded by an alanine. And you can see in this case, oops, sorry, let me bring this back. In this case, we have two scenarios, two potential options, right? This is a vast improvement, though, over the valine that we saw earlier that could have had 5 or 6 matches. Here, we only have 3. Now, before I go any further, I do want to cover how you would assign a peak in this case. Let's say that we know for a fact that this is in a serine. We'll say the alpha is a little higher, it's at 62. To assign this peak, what you want to do in SPARKY is type in AT. And here the group is, let me bring this back up. Here, let's go back to this AT. Let's say this is actually this threonine. And in this case, it's threonine 151, 2, 3, 4, 5, 6. This is threonine 156, the nitrogen, and threonine 156, and the atom here is the hydrogen. So if you click apply, you'll notice this label shows up. You assign the side chains the same way. You pick a peak there, you click AT, and the nitrogen is again the same, threonine 156, threonine 156. And the carbon is threonine 156, the group, and the atom is C alpha for your HNCA. Now for the I-1, it's the same thing. Its nitrogen is going to be the nitrogen of the peak that you're looking at. So we're going to have this nitrogen and hydrogen be T156. But the carbon here this time is alanine 155 C alpha. And for the HNCACB, you can assign these in the exact same way. For the betas, it's again a very similar process, right? The nitrogen and hydrogen are going to be, oops, for the peak you're looking at. And this is going to be threonine 156, this time the C beta, because this is the beta peak, the negative. And up here, this is going to be the threonine, this threonine, and alanine 155 C beta. So this is how you would theoretically assign this protein if you knew for a fact this is the value that it had. But let's say this isn't enough and we go back to a previous scenario where we can actually assign it. So to delete peaks, you can just highlight and then click the delete button on your keyboard. So let's remove these assignments that we just made. But let's repick this peak. So the question is, how do we know, how can we answer this question now of, we know what type of amino acid it might be, but how do we know which one it is? Is it a threonine or is it a serine? As I said earlier, this is where we start looking at the sequence in the I-1s and start answering the question of where in the sequence is this? We can see here that in this threonine, the alanine here, its I-1 is a leucine. If we look at the scenario where we have the alanine and serine combo, we see here in one scenario, the alanine's I-1 is an alanine. we can see in another scenario, the alanine's I-1 is an isoleucine. So if we can find in our NHSQC here, if we can find the peak that corresponds to the alanine that we see its I-1 C alpha and C beta values here, then we can see its I-1 values and we can determine and resolve this ambiguity. Is it AS? And if it is AS, which one of these two cases is it? Or is it the AT? Based off of the C beta values that we see, C alpha and C beta values we see. So to do that, we want to run what's known as a strip plot. And to do that in Sparky, you can type in SP. Why is this not showing up? SP. So we can see this strip plot showing up here. And what you want to do is go to Show, select Strip Spectra, and in this case, we'll click the HNCACB. What this does is you can set two values. Actually, you can set as many values as you want, but you set a value, right? And this program will then search through all of your strips for every single peak here to find peaks that have the corresponding same value. So for example, I can go here in my peak picker and I click the 60.33. And then if I click plus peak here, it will show up. If I zoom in, this might be hard to see, but unfortunately there's no way to really enlarge this. And you'll see the HNCACB here pops up. And what it will do is it will search all of the other strips within your HNCACB for every amide you have here to find strips that have the same C alpha value. If I pick both the C alpha and C beta peaks, if you use the shift button, you can highlight both of them, and then I click peak. This will search both the C alpha and the C beta peak, right? But in this case, we want to find the I-1's strip. So instead, what we would do is pick the I-1 C alpha and the I-1 C beta. And make sure, again, these are both selected. You can do that by holding the shift button. And if you click peak, these will both pop up. Now, if I click match, this should go through and search all the strips for a match. And you'll always, of course, get your own strip back because your own strip is always going to be a match. However, you'll notice in this case, there are no other matches found. No other strips contain that C alpha and C beta value. The reason why we got no matches is because Sparky does not actually know that this is a peak. It does not identify this as a peak just yet. It is not searching based off of looking at these contour levels and trying to identify what's a peak and what's not a peak. Instead, what it's searching is your peak list, the peaks that you have picked. So the very first thing that you actually want to do once you get your 3D data like this set up and started is you want to go through every peak in your NHSQC here. You want to pick the peak for your amides and you want to pick the peaks for your 3D data. So in this scenario, for example, I want to pick this peak and this peak in the HNCA. And the HNCACB, I want to pick all four of these peaks. Then I want to pick another NHSQC peak, such as this one down here. Click VC to go to it. And pick this one, and again, pick both peaks, your I and I-1s in your HNCA. And pick all four peaks in your HNCACB. So in this case, we have a C beta right here at 42. Now, as you're going through picking all of these, sometimes you may come across regions. So let's pick this one, for example. You might come across regions where you have overlapping peaks. Right, so let's pick just this and this, for example. And here we don't obviously have a C beta because this C alpha I-1 is an alanine. So let's find a scenario that you might have overlapping peaks, potentially somewhere like here. Okay, here looks to be potentially more than one peak. Sorry, this is a little slow. Yeah. So here you can see in your HNCA strip that we have an I and I-1 here and an I and I-1 here. Now these are generally pretty well resolved, but if your strip here is wide enough or small enough, you'll see both of these peaks. It's important to note that your I and I-1 are always going to have the exact same proton value. So, for example, in SPARKY, you can actually draw a vertical line. So if we draw a vertical line here through this peak, you'll see that these two line up, and if we draw a vertical line through this peak, you'll notice that these two line up. So these two are for this peak, and these two are for this upper peak up here. Right. So that can be if your resolution isn't that great, if you have peaks that are close together, you can try to use these vertical lines to line them up when you're peak picking to determine which one correlates with which. Sometimes, in many cases though, let's find one such as this one. So in this scenario, right, we have two peaks whose proton values are basically almost identical. You can see, there might be, maybe if I zoom in here, you can sort of see this. There might be a little deviation, but they're pretty close. And so it might be difficult in this case to go, okay, which C alpha goes with which one, and these C betas, which one goes with which. Now it's important to note that as you move through the nitrogen plane, the closer you get to the center of the peak you're looking at, the stronger these peaks are going to get. The further away you are, the weaker the peaks are going to get. And so you can use this as well sometimes to determine exactly what you have going on and differentiate between these two peaks. So let's bring one a little up here in this case, and let's bring one down here. So if we do VC and go to the plane that's maybe a little lower here, we can see that all the peaks have generally gotten weaker from before, but we can see this peak up top, for example, is still pretty strong, and so is this one. So these two are probably the eye of our overlapping peaks. However, which one coincides with this peak, which one coincides with this peak? If we go VC to this peak, we'll notice if we jump here and here, this hasn't changed all that much, right? The peak at 52.5, let me go in a little more, but you can see that the one at 55.5 has changed substantially. You can also see that the I-1 peak, the one that is at 54.5, has increased substantially, but the one at 55.31 hasn't changed all that much. So we can determine that this peak and this peak here and here coincide with this bottom half. We'll have to move this a little over here to the right. And we can see that this peak at the top, this peak right up here coincides with this one and this one. And we'll have to move it a little over here. So we've been able to determine now which of these C alphas correspond to these two peaks that were overlapping, and now we can determine their centers. We can apply the same philosophy with their betas. Here we can see we have three betas that are pretty overlapping. But if we jump down, we can see that this one at 40.45 and 35.7 have significantly decreased, whereas the one at 31.45 hasn't changed all that much. But if we jump up, we can see that these two peaks start to get significantly more intense, the one at 40 and 35, but the one at 31 hasn't changed much. So we can assign, or we can determine that these two peaks correspond with this top one, and this bottom peak, or this one at 31.5, corresponds with this bottom peak. If we go here, we'll also notice a peak here and here. Doesn't change all that much. So you can also pick that one to be corresponding with this one. Now again, it's important to make sure that these perfectly line up with the peaks that you're picking. So you can see here that the two C alphas that we have picked and the two C betas that we have picked line up perfectly. All right. And let's check with these other two that we also picked and make sure that their C alphas line up with their C betas. So you can see here, using both the hydrogen values, making sure they perfectly line up, and the intensity differences jumping between planes. For peaks that are overlapping, we can sometimes use these tips and tricks to determine which C alpha goes with which C beta when we're picking peaks. And this is incredibly important to make sure that you pick the peaks that correspond with the proper peak in the NHSQC in your sidechains. Sometimes you can't really differentiate them, and in those cases it's perfectly fine to just pick all of them in the same as the same peak. So in this case, let's say we couldn't distinguish between the two and we just had one peak over here. It would be fine if in this scenario you just picked all four, right? And same thing with the C betas and said, these guys are just overlapping, I cannot distinguish the two. That's perfectly acceptable. There are many cases where you might see that as well. But ideally, if you can resolve which ones fit with which, it'll make your life a lot easier. So, like I said, the very first thing you want to do is go through every peak in your NHSQC and pick it, and then go through the respective strips and pick every peak you see there, the I and the I minus ones. Now that all of your peaks are picked, we can begin with starting to assign this protein. Now in my case, I've already assigned this protein, and so all the peaks are picked and they all have labels, but let's assume in this case that these peaks are not actually assigned. So as I said earlier, generally you like to start with glycines as a starting point. So let's just pick this random glycine over here, glycine 212. Now we can see here we have two peaks. You have the I peak that's at around 46, which makes sense, it's a glycine, and an I minus 1 at 57. We can see the same I peak here at 46, and I minus 1 at 57, and no I minus 1 C beta. This is probably not a good example. Let's jump to this one. Okay, so this is a much better example to start with. Glycine, as expected, like I said, glycines generally show up here. And then in I minus 1, where the C alpha is 54.85 and your C beta is around 40.0. Now I have this labeled as aspartic acid, but if we look at our list here, right, you could have asparagines, aspartic acid, leucines, phenylalanines, tyrosine. So there's a number of different amino acids you can have. So how do we distinguish which one we have? Well, if we look at our sequence again, and we look at the glycines, we can see we have a number of glycines. We have a glycine whose I minus 1 is a valine. We don't have that scenario here. We have a glycine whose I minus 1 is asparagine, so that is a possibility. This peak could be glycine 31. A glycine whose I minus 1 is a leucine, so that's a possibility. Can't be a serine, it's not an arginine, it's not a valine, not a lysine, not a threonine. So, you know, you go through your sequence and you look, and you can see that it could be this DG here, an aspartic acid glycine, or it could be this leucine glycine. So there's a number of scenarios. So let's try and see if we can find the I strip for this I-1 amino acid. And to do that, let me get rid of this, we use a strip plot. So we can highlight both of the peaks of the I-1 peaks, the alpha and beta, and type in SP. And we want to search the HNCACB. So I can click peak, and then if I click match, you will see here, sorry, this is, unfortunately you can't really enlarge this even if I try. But you can see here that you match with itself, of course, and there is one other strip that has a C alpha peak at 54.85 and a C beta peak at 40.0. And keep in mind, when you're looking at these strip plots, if you're going backwards and looking at the I-1s, it is important that the strip you're looking at, the C beta and C alpha, be the I of that strip. What I mean here is, if I go to this strip, so we can see here that its coordinates is 120.2 and 8.148. You can bring up your peak list using LT, and this shows your peak list here. So if I click LT here on the peak, it'll show me the coordinates 120.196 and 8.146. So if I double click this and I zoom in, we can see it comes to this peak down here in the NHSQC. And we can see in this scenario, if I look at this strip, that the I that we were looking at, or the I-1 we were searching in that glycine, is the I of this peak. Because, actually there's no I-1 here. Because the I-1 for this amino acid is a glycine. Right, if we look at the I peak here, the stronger of the two, 54.8, this is what we had searched. And the I-1 is 45.3. So now we know that this peak down here and this glycine that we had up here are connected. This peak is in fact the I-1 amino acid of that glycine. So let me bring up the sequence again. So we saw here we have multiple scenarios. We had a glycine whose I-1 was an asparagine. We had a glycine whose I-1 was a leucine, right? And glycine here whose I-1 was an aspartic acid. And here a glycine whose I-1 was also a leucine. So we couldn't differentiate just looking at that one peak. But now that we are looking at that I-1 strip, we can see its I-1. So we can see here that the I-1 of this peak is a glycine. So now we have a glycine that is preceded by either a leucine, an asparagine, a tyrosine whose I-1 is also a glycine. So if that's a little confusing, don't worry, we'll go through it. So right now, if the glycine we were looking at was glycine 31, we are now looking at its I-1 here, which is asparagine 30. What we should be seeing in the strip right here for the HNCA, is, let me bring it back, we should be seeing an alanine. However, alanine betas show up at the 20 region. This doesn't have any betas there. And we can see here that the I-1 for this peak is a glycine. So it cannot be, that was not glycine 31, and this is not asparagine 30. If we look here, what if we say that was glycine 35? And the peak we're looking at here is leucine 34. Well, if we look at the I-1 of this leucine, we see it's a serine. Again, we know the I-1's a glycine, so it can't be that. And if we look throughout all the other glycines we can see here that we have a glycine whose I-1 is a aspartic acid, which makes sense based off the chemical shift values we've seen. And we see its I-1 is a glycine. So that matches exactly with what we see. Finally, just a final check, if we look at this glycine, whose I-1 is leucine, we can see that its I-1 is a methionine. Again, we know that it should be a glycine. So now we can assign these two peaks. We know that this peak down here is aspartic acid 229. And we know that the glycine that we came from, the one we looked at initially, the one that is up here, is glycine 230. This is what's known as walking backwards, I believe, or looking backwards, or going step by step. There's a terminology for it, I forgot. But basically, you start with an anchor point, generally, like I said, glycines, alanine, threonines, amino acids that fulfill that first requirement. It's very easy to immediately find out what amino acid it is. Then you look at its sequence and try and determine, okay, where in the sequence is this glycine based off its I-1? You use a strip plot to then use that I-1 and go backwards, right? And find out where is the I peak of that -1. So in this case, we ran a strip plot and we saw there was only one amide in our NHSQC who had a strip that contained a C alpha and C beta value that we see here matches this I-1. And that was the aspartic acid, this peak right down here, right? So now we want to continue to go backwards, right? Let's see if we can find that glycine, this glycine 228, and its I-1 should be a serine. So we do the same thing. I can click here, the peak that I want to search, type in SP, again, show. We can search the HNCACB or the HNCA. You can search whichever one you want. You click peak and you click match. Now here you can see that we have a couple of matches. The first is a peak here that matches over here with this glycine. But I hope you can see this. You'll notice that this is matching to a negative peak, which that's not correct. We're looking for a glycine which should be positive because it should be the C alpha peak we're looking for. So we know this match is not correct. We can get rid of it by highlighting it so it has this blue box around it and minusing the selection. If we go to the next match we got here, we can see that this is also looking at a C beta. We should be looking at a C alpha. So we can click over here and get rid of it. Here we can see that we're matching finally to a positive peak, and if we look, making sure again, this peak we're looking at in this strip should be the I peak, so it should be the most intense peak we see. If we look down within the strip, we can see that there are other peaks, but they are weaker than the peak that we're searching for, which makes sense. And we can also see that you have a peak here at around 60.36 and a peak here, a beta, at 63.83, which, if I bring up the average ranges here, an alpha and a beta at around 63 matches with a serine, which is exactly what we would expect this to be. So we can go to this peak. If I click LT and I go to it, to this glycine here, and now I can assign this peak as glycine 228 and assign the peaks here and the HNCACB. And so through this step, we have now assigned these three amino acids. We've assigned the glycine, the aspartic acid, and the glycine as well that comes over here at 228. We can do the exact same thing to assign the serine. We can again click both the C alpha, C beta, peak, match, and we can see that there's only one peak and one strip that has the same C alpha, C beta. Again, we want to do the proper checks. We want to make sure that there is no other peak that is stronger than the peak we're searching for here. And because we're looking for the I peak in this case. And we'll see there's another peak here, but it is weaker, so that's good. And there's another peak here, but that's also weaker. And in fact, just looking at the chemical shifts, right, we can see here the I-1 here is around 54.7. And the I-1 here is at around 18 or 19, which coincides, if we look with a beta at 19, the only thing that could be is an alanine based off of the chemical shift of that C beta. And if we look at our sequence that we're looking at, we can see here that that serine, its I-1 is an alanine. So this makes perfect sense. And now we can go to the strip here. We'll just click on the peak, LT, and this peak here is serine 227. Now I have it assigned as such. Normally there won't be an assignment, but you can just type in AT here and assign this as serine 227. And we can continue working backwards to basically assign the entire protein in this manner. So now you've assigned 4 amino acids. Then you can go to the alanine, assign that. Go one more back using the strip plot, assign that. Go one more back, assign that. Sometimes you may hit walls where you have multiple matches. In this case, we've been lucky where we've only had a single match. Sometimes you might have multiple matches. And in those scenarios, you might have to go and search multiple different scenarios and settings. For example, let's see if we can find one. So, in this scenario, all right, we're going to do the same thing. We're trying to use an anchor point, so we can see here based off the C beta at 18.62, which is the strongest C beta here, so it's the I peak, and a C alpha at 54.06. Again, it is the stronger of the two peaks, so it's the I peak. We have an alanine, just based off of, again, if I bring up this list, based off its chemical shift value. No other amino acid has a C beta at 18. So let's try and find out which alanine this is. So in our sequence, so we'll pick the I-1 C alpha, and we'll pick the I-1 C beta over here, and we'll type in SP, bring up the strip plot. We'll search the HNCACB, click peak, click match, and again, you match with yourself. And now we have 2 other matches that we found. So let's do a search here and see. Here we can see this is a C beta, but very weak. But there is no other C beta here. And the C alpha is also very weak, but it's the only C alpha, so it makes sense. This is the I of this strip, which is what we're looking for. If we look at this peak here, we can notice that in this scenario, this is a weak peak, the one that we're searching for in this strip. And there's another C beta that's actually stronger. So we know for a fact it's definitely not this peak over here, so we can actually get rid of it. It's not this strip. So now we know, okay, this is the preceding strip that's behind it. So if we go to it, oops, I'm sorry, I forgot to click it. If we go to it, and we look here, we can see that we have no I-1 C betas. And if we look here, we can see that we have a I-1 C alpha at 59.7. And that's the only C alpha that we have. So if we look at our sequence, we said we have an alanine. And based off of the chemical shift values here that we have at 38.0, we can see that we have an alanine that should be preceded by either asparagine, aspartic acid, leucine, phenylalanine, or tyrosine, just based off the alpha and beta values. And if we look at our chemical shifts here, we can see that we have a leucine preceded by an alanine, so it could be that. Phenylalanine preceded by an alanine, or sorry, a alanine that preceded by a phenylalanine, it could be that. Another Al situation here. So you have multiple different potential options. And you can see here that we have an I-1 that is at 59.7 and no beta. And so if we look at our setup here in our sequence, we see that this leucine, for example, or the peak that we're looking at, has an I-1 of valine, right? 59.7 is a little bit outside of valine's range, but it should be noted these aren't exact. You can have slight fluctuations outside of their ranges. So it could potentially be this valine. If we look here, you have a alanine that precedes this leucine here. Or sorry, I skipped this phenylalanine. You can see you have a threonine that precedes this phenylalanine. And if we look here, threonines could also show up at around 59. And so we already have two potential options that we can't quite eliminate. And again, this one has a alanine that precedes it. Alanines, 59 is too high for them, so we can cross that out. You have isoleucines. Those generally are a little bit higher, you can see here, but could potentially be an isoleucine as well. So we have multiple options here. We know we have an alanine, and we've been able to find its I-1, but because of the quality of our data, we are still not able to assign it. So we need to go one more step backwards and see maybe we can find this I-1's strip in this peak. So we do the same thing. We click here on this I-1, C alpha, and this time let's search the HNCA only. We click peak, we click match, and you see you have 10 matches here, right? You have 10 different strips that have C alpha values that line up with the C alpha value you are searching. Now, this is quite a lot, but some of them can easily be crossed out. Because we are searching the I-1 of this strip, what that means is we're looking at the I of our matches. So it has to be the stronger of the peaks, of the two peaks that you'd normally see in an HNCA. Now in this first match, we can see that this is actually overlapping. So we can't cross this out because while it is weaker than some of these peaks, it is also stronger than other peaks. So it might be the I of this strip. It's unclear. If we look at this one, we can see there's a peak up here and a peak down here, and this is the stronger of the two. That's good. That's what we expect to see. If we look at this one here, you can see that this is actually the one that's searching is the weaker of the two. So we can get rid of this match. It's definitely not that one. If we go here, we can see there's one peak and there's two peaks, right? But the one that we're searching for, this peak here at 59, is the weaker of the two. So we can get rid of that one as well. If we come here, we can see that there are two peaks, and this is the stronger of the two peaks, so that's good. We can keep that match. We go further here, we can see that, let me get rid of this label here. You can see that this is one, and that's actually the only peak in this one. So this is also the I of the one we're looking for, so this is a good match as well. And you basically continue the same thing, right? We can get rid of this one because it's the weaker of the two. And then this one we should keep because it's the stronger of the two. And this one we can get rid of because it's the weaker of these two peaks in the strip. So now we've gone from 10 to 5, right? Just by looking at, is this the I of the strip that we're looking at? Now in this case, there's a couple number of things you could do. You could go to each strip and look at the C beta and see if it makes sense, right? So as we said, here we have, say potentially if we think that this is the leucine, leucine 7, we would be saying that the I-1 is a valine, right? So the matches that we're seeing here are valine. So we can go to each of these matches that we've seen and look at that C alpha and C beta, right? You see here that this one has an I, C beta at 30.3. If we look here, valine 30.3, this is a good match, if that's what we have going on, right? If we go to this peak over here, if we go to another match, we see that it has a peak at 29, but it has a I peak at 72. That doesn't match, right? So if we suspect that we're looking at leucine 6, then we would be getting rid of this. However, you'll notice that I actually have, if I go back to the peak that we have assigned, I have this labeled as phenylalanine 15. And that's because what I ended up doing is I went through each strip and I went backwards for each of them, right? I looked at the valine and I looked at its I-1 of these matches and I said, does that make sense, right? I looked at the matches here and I looked at their I-1s. So for example, I looked at this threonine and I looked at its I-1 and said, does that make sense, right? So for example, right, if we're saying that this is leucine 6 and this match that we have is for the valine right before it and we go to it, the I-1 of this peak, based off our sequence and based off what we suspect might be, should be a glutamate. Glutamates have alphas at around the 54 and betas around the 29-30 region. They're I-1s. So if I look here, I can see that I have a C alpha peak at 66, right? So if we suspect that we have the valine, while the C alpha and C beta of the I match and make sense, the C alpha of the I-1 doesn't make sense. So we can say right off the bat that at least for this match, we don't have a valine there. Now I would have to check each of these matches and look at their I-1s to see whether or not this series of valine preceded by glutamic acid makes sense, or sorry, glutamate makes sense. This, of course, takes a long time and is pretty tedious. So usually what people do at this point when you have a lot of matches and there's a lot of things you have to go through, you can either use other experiments, which we will be covering, to help in determining which one you have. You can use chemical shift predictors, which we'll also cover, that will help explain and assist in understanding which setup you have here, what amino acid you have. And you can also just start with a new anchor point. Say, okay, this is going to take too long. There are too many matches. Let me look at another peak here. Let me look at maybe another threonine, or let me look at another glycine, or we started with an alanine. Let me try and find another alanine and start from there going backwards to the I-1. Or if you want to stick with the same one and you don't have any additional alanines, and you don't have any additional anchor points that you can use, you can also go forward. You can start using the strip plot to look at I+1s. So what we've been doing previously is searching for the I-1s here. But instead, what you can do is search for I+1s. So instead of picking the I-1 peak, you click the I peak here. So we pick the alanine at 54, it's C alpha, And we click the alanine C beta here at 18.6. And we search the HNCACB again, peak, match, and you see we only have one match here, which is good. So if we go to this match, we can go here to it, and we can see again our alanine I-1, but the I of this peak has a C beta at 43, and it has a C alpha at 54. Right? So we tried, let me enlarge this because this part's really important. So we had tried previously to go backwards. We had an alanine and we knew its I-1 was a leucine, a phenylalanine, a tyrosine, or an aspartic acid or asparagine. We knew it was one of those 5 options. But we had multiple scenarios where you could have that. We went one further back as well, and we were able to find the I-1 and look at its I-1, but since we only had a C alpha in that case, it was difficult to try and just assign those peaks based off those 2 pieces of information because we had so many matches in our strip plot. Going forward, however, we can see that the alanine, it has a leucine, asparagine, or aspartic acid or tyrosine in its I+1. So we can see here, for example, we were looking at this VLA setup here. This I+1 is an arginine. And like I said, we know its I+1 now is either asparagine, aspartic acid, leucine, tyrosine. So we know that we don't have this setup. If we look at the I+1 of this alanine, you have an aspartic acid, right? And the I-1 also makes sense because it's a phenylalanine. So it fits the category that we just discussed. If we look at this alanine here that is preceded by a leucine and followed by an asparagine, that setup also fits the criteria that we had. However, if you recall, let me go back, we had found the I-1 of that alanine, right? That was this peak here. And we saw that its I-1 was at 59. And if you look at our list here, 59 is too high for an alanine. So, based off of that, we know that this leucine's I-1 is an alanine. We know we don't have that. That doesn't fit the other criteria based off the data we've seen. So we don't have this setup either. If we look at this alanine, its I+1 is a tyrosine, which makes sense, but its I-1 is a histidine, which doesn't match the criteria, right? And across the board, right, as we can see, this IAR, that doesn't fit our criteria. The LAK, that doesn't fit the criteria. This TAT, that doesn't match. And if you look throughout everything that we can see here and all of the potential scenarios and options, this FNAL might work. Phenylalanines can have C alphas at 59. And this matches our criteria for the I-1 and I+1 being either asparagine, leucine, tyrosine, phenylalanine. And we can see, based off of the rest of this protein, that no other alanine fits. Actually, this one fits, right? The arginine can have an I-. It can have a C alpha at 59, and this DAL fits the setup we were looking for. So now we've gone from, say, 10 options to 3. Either it's this RDAL, it's this TFAD, or where was it? There was one more option that we had here. Actually, I think that was it. Oh yeah, this FNAL. So it could be these 3 potential options. However, if we look at the I+1 and we look at its I+1, we can see here it's a leucine, here it's a valine, and here it's a serine. So you can see if we can actually jump one more forward and we can find out what the I+1 of this, let me go back. If we can find what the I+1 of this peak here is, then we can assign this series of this chain of amino acids. So we do the same thing. We click on the I peaks in the HNCACB. Here we go. And we click on both of them. And then peak match. We can see here that unfortunately we seem to have hit a wall. And there are no matches. Now, when going forward in the I+1 direction, it's important to keep in mind that you're looking for strips where your matches are I-1. So inherently, they're going to sometimes not show up because they're going to be weak. So as a result, sometimes if you don't get a match in your HNCACB, you should also check your HNCA. That's a more sensitive experiment. And look for the I+1s here. In this case, we have 14 matches, right? But as we said, in our matches, what we're searching should be the I-1. So if we go to this peak, for example, we can see here, if we go up and down, we have this I peak that it matches with. And we can see there's a second peak, but it's weaker than this one. Now, since we're going forward, we're looking for our matches to be the weaker of the two peaks in your HNCA. So it's not this one. If we look at this peak, we can see that our match is in fact weaker than the two peaks, which is good. That's what we're looking for. So we can keep that. We can see here that it is also weaker of the two peaks. So that's good. And we can see here that, sorry, there's labels sort of covering it. This might be an overlapping peak, so we'll have to check it individually. We can't eliminate it as a result. And here we can see that this is also a match. So at this point, this is getting a little messy, right? We have at least 4 options, and I haven't even looked at the other 7, 8 matches to see whether or not we can keep those or get rid of those. So at this point, we've sort of hit a wall, and so we can go back to what I said earlier. You can use chemical shift prediction software. Those can tell you whether or not you have the correct, or tell you where in the sequence this chain you have is to help assign. You can use other information of other experiments, which we will cover, or you can just say, okay, I can't go anywhere with this. Let me leave this alone and try assigning other peaks. Because as you start to assign other peaks, you might actually find out that you can eliminate your other options. So just hypothetical. Say I have assigned all of these other peaks, and these two strips I have not assigned. Everything else I've assigned. Well, I can get rid of them because I can say I've assigned this. I know that it's not this because I know I haven't assigned the I+1 of what I'm looking for in those 3 setups. Then I can start subtracting these and saying it's definitely not these matches, and so now I only have 2. So when you hit a wall like this, sometimes it's best to just write down the chain, write down this link that you have, go assign the rest of your protein and your other peaks, and then come back to it. You might be able to eliminate a substantial amount of these matches that you got and be able to reduce it to maybe 1 or 2. And in doing so, then you might be able to actually assign this series of 3 that you have. But this is the basic theory and philosophy behind how to use your 3D data to assign your spectra. And in fact, I believe the site has a nice diagram that shows this. If we go to maybe assignment theory, nope, that doesn't show it. Visualizing, or maybe, sorry, triple resonance backbone. So you can see here, this is effectively what we've done, right? This is why I said I like to cover the practice first and then the theory. We looked at an I peak of an amide, right? And so this is a glycine, and what they're doing is they're searching the I-1 of that glycine, which in this case is a serine or a threonine, right, for this amide. They found a peak, right? They found a peak here whose I peaks match what they're looking for, and it has an I-1 of alanine. And so they then did a strip plot, searched through all the strips, and found a peak whose beta and alpha matches what they were searching for. And in the strip of their match, it is also the I of the ones they were searching for, so that fits. And they just sequentially go down and using the chemical shift values determine what these peaks might be, and then they look at their sequence and go, where do I have an alanine, or where do I have a glycine preceded by a serine or threonine preceded by an alanine, and assign their peaks using that. This is generally what's done for assigning the backbone. So that wraps it up for this video. There are, of course, a lot more different scenarios that one might hit, but again, this is just supposed to be a basic guide to get you started. Assignments are one of those things that it's just experience. It comes to you, and after a while you start to see the patterns and trends and get a feel for it. In the next video, I will be covering additional NMR experiments that one can use, such as CBCONHs, HNCACOs, as well as NOSIs, to help assist in the assignment and what their pros and cons are and why you might want to run them.